Okay, I'll get started. Last class, Tuesday's class, we talked about relativity. This class, Thursday, we're also going to talk about relativity. In Tuesday's class on relativity, we talked about the foundations of relativity, and then we talked about the core ideas of time dilation, length contraction. In today's class, I want to walk through these three bullets on relativity that develop out of those foundations of relativity. I want to talk about speed in relativity, and I want to talk about a natural or nature's speed limit that emerges in relativity. That's a fascinating thing. I want to talk about the laws of motion in relativity compared to the laws of motion in classical Newtonian physics. We've modified ideas, notions of space and time. We're going to have to modify ideas, notions of laws of motion. To do that, I'm going to focus on updating our conception of energy. So we're going to change that and update that. And updating our conception of momentum. We're going to change that. We're going to modify that. And so this is the plan. I wanted, because relativity is so strange, relativity is so counterintuitive, I just wanted to remind us of the major points from last class, because they really are the building blocks of today's class. So we started last class with discussion of the foundations of relativity, the ideas behind relativity, and there were two of them. One was that the laws of physics are invariant, absolute, the same for all observers in all reference frames. And the other one, strange one, was that the speed of light is invariant, absolute, the same for all observers in all reference frames. The whole of relativity is based on those two statements, those two ideas. We said that to explain the fact that light has the same speed in all reference frames, we have to modify, change our notions of space and time, and we introduce time dilation and we introduce length contraction. So those are the two key results in relativity, time dilation and length contraction. Time dilation is the fact that the time interval between two events, that's kind of the duration between two events, is dependent on your frame of reference. That's not true classically. It's the same in all frames of reference. And the fact that the time between two events depends on your reference frame is a very strange thing about relativity. So that's time dilation. And the quantity of time dilation was quantified by this parameter that we called the Lorentz factor. We gave the notation gamma, and it relates the dilated time to the proper time. There was a similar effect for space intervals, or distances, right? The distance between two locations, right, in New York and Paris. Classically, the distance between New York and Paris is absolute. It doesn't depend on your reference frame. In relativity, it's frame dependent. It depends on your reference frame. Again, so there a parameter, the Lorentz factor, determines the distance between Paris and New York in different frames. It determines this effect we call Lorentz that we call length contraction, and here's the equation that went with length contraction. So again, this is another second really strange feature now of space. We looked at an example of time dilation and length contraction. The example we looked at was an astronaut's travel to a distant planet. In the astronaut's travel to a distant planet, there were two reference frames. There was the distant star. There was the astronaut reference frame in the space rocket, and then there was the spouse's reference frame back on Earth. So those are two different reference frames, and we discovered that in accord with our ideas of time dilation, our ideas of length contraction, that they would measure different times for the length of the trip, that's the duration of the trip. They would measure different distances for the distance traveled on the trip. And here I've just quoted the results from that calculation in the last class. If the astronaut was traveling at 95% of the speed of light, okay, so that's very fast. That's close to the speed of light. So relativistic effects are big effects at 95% of the speed of light. We found that the astronaut measured the length of the trip from leaving Earth to arriving at Alpha Centauri to be 1.4 years, and measured the distance to be 1.3 light years. So that's the astronaut measuring how long it took and how far they went. On Earth, the spouse measured the trip with the spouse's reference frame. The spouse measured the trip to take 4.5 years, much longer. The spouse measured a distance covered for the trip from Earth to Alpha Centauri to be also longer for 4.2 years. This is telling you that because of time dilation and length contraction, these two observers in these two different reference frames are measuring very different distances and measuring very different durations for the trip. The astronaut measured what we call the proper time for the trip. We call that T0. That's the proper time for the trip, because the proper time is between two events, is where the frame in which the events occurs at the same place. And for the astronaut leaving Earth and arriving at Alpha Centauri is actually at the same place, because their reference frame is glued to their spaceship. And so they leave Earth at the origin of their reference frame, and they arrive at Alpha Centauri at the origin of the reference frame. They've measured the time interval in a frame where the events arrival and departure and arrival took place at the same location. So they measured the proper time. On the other hand, the spouse at home measured the proper distance. The proper distance is measured when the object you're measuring the length of, in this case it's the length of a tape measure that runs from Earth out to Alpha Centauri, so it's a very long tape measure. You measure the length of the tape measure in the frame where the tape measure's at rest. That's where you measure the proper length. The Earthling is seeing the spouse on Earth. They're both Earthlings. The spouse on Earth is seeing the Earth at rest, Alpha Centauri at rest, the tape measure at rest. So that person is measuring the proper length of the proper distance for the trip. And so that's why we call that L0. If you were to take the time taken divided by if you were to take the distance traveled divided by the time, that's velocity. That's a law of physics that says velocity is distance traveled divided by time. And you'd find that if you divide in either case, for the astronaut or for the spouse, if you take distance divided by time, you get a velocity, and it's the same velocity in both cases, 95% of the speed of light. The spouse is seeing the astronaut travel at 95% of the speed of light, but also the astronaut is seeing the spouse travel in the opposite direction at 95% of the speed of light. That's an example that the laws of physics, that's velocity is distance over time, they are invariant in both of these reference frames. Okay, I spent a lot of time recapping there, but we are going to use all this today, and it is a very difficult conceptually to understand relativity. Okay, let's talk about adding velocities, and let's talk about nature's speed limit on the maximum velocity. This is our first bullet. Let's take a look at this picture here, this slide here. It shows two reference frames. There's a reference frame of the pedestrian standing on the roadway, and there's a reference frame of the passenger in the truck. So there's these two different reference frames. They're moving with respect to one another. We met this picture last class. In blue here, labeled with X and T for the coordinates, that's the reference frame of the pedestrian, and in green here, that's the reference frame labeled with X prime, T prime of the passenger. So these are the two reference frames. And I'm actually drawing this was a choice I made. I drew it from the perspective of the pedestrian rather than the passenger. I could have done either. It's drawn from the perspective of the pedestrian rather than the passenger because the passenger's reference frame is moving with respect to the pedestrian reference frame in this picture. And this V subscript R is the velocity of the passenger reference frame. Now, what I've added to this picture is the little birdie. That's the only thing I really added to the picture. The little birdie is flying ahead of the pedestrian and the passenger, and they're watching the little birdie, and they're thinking about how fast is that birdie flying. Here's the birdie, and here's the velocity of the bird. As seen in the Vx is its velocity or speed in the pedestrian reference frame, so that's the color coding, and the green Vx prime is its velocity in the passenger reference frame. And the question I'm posing about velocities is if we say we knew the velocity of the bird in the pedestrian reference frame, supposing we knew that, how would we calculate the velocity of the bird in the other reference frame, the passenger reference frame? So we know Vx, the blue Vx. How do we calculate the green Vx prime? What's the bridge between the two reference frames? Well, in classical motion, in Newtonian motion, the answer to that question is actually just common sense answer to that question. It's this equation here. That the speed of the birdie in the passenger reference frame in green is equal to the speed of the bird in the blue reference frame, the pedestrian reference frame, less the motion, the speed of the passenger reference frame in the pedestrian reference frame. That's the VR here. It's just this equation here. It's really common sense if you think about it. You already knew this equation when you were 4 years old. If the truck was going at 10 miles an hour in the pedestrian reference frame, if the birdie was going at 30 miles per hour in the pedestrian reference frame, then in the truck reference frame, which is catching up with the birdie, you would see that the bird is traveling in the passenger reference frame at 30 miles per hour less 10 miles per hour. That would be 20 miles per hour. That's completely obvious. You knew it when you were 3. Unfortunately, in relativity, that's not the case. It's not true. There's a different transformation of velocities from the passenger to pedestrian reference frame or between two reference frames when the motion is not negligible compared to the speed of light. So this is a different velocity transformation. The last one we called a fancy word, Galilean transformation. Is just common sense transformation of velocities. Another fancy word, Lorentzian transformation, after somebody called Lorentz. This is the relativistic transform of velocities. Picture's exactly the same. Question's exactly the same. How fast does the passenger see the bird traveling when we know the speed that the pedestrian sees the bird traveling, and we know the motion of the passenger in the pedestrian reference frame? The answer to the question, though, is a different formula. It's this one down here. This is the relativistic formula. This is the one you'd have to use if the speeds were large, if the speeds of order the speed of light. We'd be working with this equation. We'll see that. Over here, the left-hand part of it looks exactly actually like the previous formula, except on the right-hand side, I'm dividing by this kind of strange, I think, quantity. It's a weird quantity. Where did it come from? It came out of time dilation and length contraction. Can't explain exactly how it came out of those two effects, but it comes out as time dilation and length contraction. It's a modification of the transform of the velocities from one frame of reference to another frame of reference, and it involves this division here. There's a couple of interesting things about this expression down here. First of all, it seems like, oh, that seems scary. I've lost all my intuition. I want to run away, or something like that. But let's look at what is in that denominator. There's Vx, Vr, and they're divided by c squared. So those are all velocities. There's a velocity squared actually in the numerator, velocity squared in the denominator. So velocities have the units in the numerator and the units in the denominator cancel each other out. This ends up being just a number. This number, if the velocities are small, supposing the velocity of the truck in the pedestrian frame is small, supposing the velocity of the birdie in the pedestrian frame, that's also small compared to the speed of light, then that quantity in the denominator, Vx, Vr divided by c squared, that's going to be very small. The denominator is just 1. You got the common sense transformation. It's only when the velocities are not small compared to the speed of light that that number becomes significant. And as that number becomes significant, right, you distort the transformation from the common sense transformation into a relativistic transformation. And it's actually, I'll just tell you this term here is what enforces, like the relativistic policeman. It enforces that you can't go faster than the speed of light, that nothing can go faster than the speed of light. So it does a remarkable job. Looks like just a little bit of wacky algebra, but it does this remarkable job of giving nature a speed limit. Let's go ahead and do some calculations with this. Okay. So this picture also has 2 frames of reference, just like the last pictures had 2 frames of reference. So I've replaced the passenger and pedestrian reference frames with Dr. Evil and Austin Power reference frames. So we just changed the 2 reference frames. Let me get these reference frames right. No. I had to write this down for myself because I wanted to remind myself of the equivalence to the last slide, and I've already messed it up. The Earth reference frame, there's 2 reference frames. The Earth reference frame is like the pedestrian reference frame from the previous example. The Austin Power reference frame, that's like the truck reference frame from the previous example. And the Austin Power reference frame is moving with respect to the Earth reference frame, like the truck was moving with respect to the pedestrian. The bird is Dr. Evil in this particular example, is analogous to Dr. Evil, i.e. we know the speed of the bird in the Earth reference frame, and we want to calculate the speed of the bird in the Austin Power reference frame. And that's what we're going to do. The first time we're going to do it twice. We're going to do it firstly calculating with Galilean velocity transformations that work at low speeds, and then we're going to do it with Lorentzian transformations that work for velocities approaching the speed of light. So we're going to see how it goes wrong here if the speeds are large, and how it goes right in the next case when the speeds are high. These speeds are large. Look, I indicated here that Austin Powers is moving at 80% of the speed of light with respect to Earth, 0.8 c. So he's going fast. He's chasing Dr. Evil. Dr. Evil is going at a speed of 90% of the speed of light with respect to Earth. And the question is, how fast is Dr. Evil going with respect to Austin Powers, traveling in Austin Powers' reference frame? So again, remember, Earth is pedestrian, Austin Powers is truck, and Dr. Evil is the birdie. So it's the same problem that I wrote on the previous slides. This is the classical transformation, that the speed that Austin Powers sees is the speed that the Earthlings see. Subtracted from that is the relative speed of Austin Powers' reference frame and the Earth reference frame. And so I can plug in the speed that the Earthlings on Earth see Dr. Evil traveling at, 90% of the speed of light. I can plug in the speed of Austin Powers, plug that in, that's 80% of the speed of light. And I would calculate, which would be common sense, right, that Austin sees Dr. Evil traveling away from him at 1/10 of the speed of light, 0.1 speed of light. Complete common sense, right? But it's not true. That's the amazing thing in relativity. In relativity, this is the calculation of how fast Austin Powers sees Dr. Evil traveling ahead of him. And it's not just the difference in these two numbers. It's not 1/10 of the speed of light. I'm using this modified equation, which is like the previous equation, but this thing in the denominator where the second piece of it gets significant when your speeds are significant compared to the speed of light. And so the only extra piece I'm putting in this calculation now is this bit here. So let's look at that. Vx is 90% of the speed of light. VR is 80% of the speed of light. Here you see the 0.9 and the 0.8 for the VR and the Vx. I didn't write all the c's down. There's a c squared in the numerator from this c and that c, but there's also a c squared in the denominator, so all the c's cancel out. This term here is just 0.9 times 0.8. If you calculate that, subtract it from 1, divide this 0.1 c by that, you get 0.36 c. So actually, if you believe it, Austin sees Dr. Evil traveling away from him, not at 1/10 of the speed of light, but actually much faster, 36%, 0.36 of the speed of light. So that's a remarkable thing that's baked into relativity. And so addition of velocities. What we've been talking about is addition of velocities in different frames. It's not as simple as the common sense intuition for addition of velocities in classical non-relativistic frames. It's more complicated, and we start to, our intuition is just melting away. And so we have to accept that. I want to show you one more example where I'm going to calculate the same thing in two different reference frames. Again, it's really the same problem as a pedestrian and passenger, as Austin Powers and Dr. Evil. I'm just making a change of the names of who the things are. Now I've got the Earth reference frame, I've got Austin reference frame, but now he's watching the light from a flashlight. And we want to see how this transforms. This is really déjà vu. Right? Because we started relativity with that discovery that every observer in every reference frame sees light travel at the same speed. So our idea is that the Earthlings on Earth looking at the light beam see it traveling at the speed of light, 1c. Austin Powers also in relativity has to see the speed of light to be the same speed, 1c. So let's assume that the Earthlings measured it, found the speed of light, 1c, 3 times 10 to the 8 meters per second. Now let's calculate, using the transforms, what Austin Powers would see for the speed of light. If I did it with the classical Galilean not correct for high speeds transformation, I would get, the light's traveling at a speed of c, Austin's traveling, catching up at 0.8c, so we'd think, well, Austin would see the light traveling at 2.2c. That would be complete common sense. But it's wrong. It's wrong. And it doesn't correspond to nature, where light always travels with the speed c. So let's use this alternate transformation. The alternate transformation has this piece is the same as the classical transformation. We've just got this little extra term in the denominator here. And so here I've got to plug in the product of the speed of the light, which was the speed of Dr. Evil, which was the speed of the birdie, multiplied by the speed of Austin's reference frame in the Earth's reference frame. That's 0.8c. So I'm plugging in 1 times 0.8 here. If I calculate this, I end up with 0.2c in the numerator. That was the classical transformation. Divided by 0.2c in the denominator. That's the relativistic effect. This is the magic that Austin also sees the speed of light to be c. So we built all this on top of time dilation, length contraction, these changes in our notion of space-time. They've modified our transformations of velocities through space and time, and they baked into themselves that light is always observed to move with the speed of light, no matter your reference frame. Okay. So now we're going to move on to our second bullet, which was to say a few words about the laws of motion. Laws of motion, classically, are Newton's laws. Second law, F equals ma, as an example. So that's what I mean by laws of motion. They describe how things move. Specifically, they describe how the motion of things is changed. So Newton's second law describes how forces change motion. That's what laws of motion really are. Now, we've just messed up space and time, or we've just messed with space and time. What was kind of an absolute space and time, absolute distances, absolute durations, has become a relative space and time with relative distances and relative durations. So we might be worried about the laws of motion. We might be worried, what are we going to do with the laws of motion? So here I've got 2 slides, which is an imagined conversation, of course this couldn't happen, between Newton, inventor of the classical laws of motion, and Einstein, inventor of relativity, about what's going to happen with the laws of motion. And it's just an opportunity to make some remarks about the nature of the laws of motion and what will change and what won't change from the laws of motion classically to the laws of motion relativistically. Laws of motion, as I mentioned, describe how forces change motion, how forces alter motion, speed things up, slow things down, change the direction of things. One thing that forces do, though, that is an underlying principle, is that forces transfer quantities we call energy, momentum, but they conserve overall the energy and the momentum of a system. So in understanding how forces work, how forces kind of change motion, it's really important to think about the energy and momentum that they transfer and the fact that those forces are conserving overall that energy and momentum. So that's a key idea baked into laws of motion. As I say, classical laws of motion are built on space and time being kind of this stage. Think about a stage in theater or whatever. The stage of space and time for classical laws of motion is one where distances are agreed on by all observers, no matter their frame of reference. Time intervals are agreed on by all observers, no matter their frame of reference. That's not going to be true. That is not true in relativity. So what's got to change in relativity? And Newton is asking Einstein, which couldn't really happen. Well, here's Einstein's reply. He makes a few points, and I think they're good points. The first point is that, sort of this bullet here, we're going to have to do something. We're going to have to do something because in relativity, these time intervals between events, they depend on your frame of reference. That's time dilation. These distance intervals between New York and Paris, they depend on your frame of reference. That's length contraction. So we've got to do something to handle that relativity of space and time. So here he says a really interesting point. So although it's going to change space and time, where things are relative rather than absolute, the idea of forces transferring energy, transferring momentum, and forces overall conserving the total energy and total momentum, although they moved it around, they shuffled it around, that's still perfectly valid in the relativistic laws of motion. So that's still a foundation of the laws of motion, that forces transfer energy, forces transfer momentum, forces conserve energy, and they conserve momentum. So we're going to keep that. All we've got to do, says Einstein, is we're just going to have to fix up the laws of motion, we've got to fix up our notions and our equations for energy and momentum. So that's what we're going to do. So I'm going to talk about momentum first. It's easiest to do it this way. That's why I'm doing it. I'll talk about energy second. It's a little bit more complicated energy. A little bit more to say. This slide here, left-hand side is classical world of Newton. Right-hand side is relativistic world, Einstein. The two columns are introducing reminding us of classical momentum and introducing relativistic momentum. So classical momentum, you'll remember, is the equation for it. Symbol for it is P. The equation for it is P equals mv, mass times velocity. The relativistic momentum of a particle, the equation for it is actually similar. We give it the symbol P again for momentum. It's P equals gamma mv. It's Lorentz factor times mass times velocity. So there's just a Lorentz factor that's popped into the equation. Look, Lorentz factor's coming up everywhere. It comes up in time dilation. There's a Lorentz factor that comes into the equation. It came up in length contraction. There was a Lorentz factor there. It's not surprising that we're going to see it when we introduce our new equations for momentum and also for energy. We'll see a Lorentz factor. Remember, inside the Lorentz factor, it's 1 over the square root of 1 minus v squared over c squared. Inside there is the velocity of something. In this case, it's the velocity of the particle whose momentum we're calculating. So this is just the little extra, he could have snuck it in and not told anybody. This is just a little extra addition to momentum. We're going to put a gamma factor in there. Still, both classically and relativistically, forces transfer momentum. They also conserve momentum. This is the second remark here. Third remark here, it's classically, the conservation of momentum corresponds to if you calculate mv for all the particles in a collision. So supposing you've got a few particles in a collision, coming in, going out. Calculate mv for each of them, and then you check that the sum of the mv's before equals the sum of the mv's afterwards, you'll find that momentum is conserved. That's classical momentum conservation. Same idea for relativistic momentum conservation. If you've got a bunch of particles colliding with one another, relativistically, if you calculate gamma mv for each of them before the collision, and then calculate gamma mv for each of them after the collision, individually the momentum might be different, but the sum of the gamma mv's before before will equal the sum of the gamma mv's afterwards. That's momentum conservation in relativity. And so that's this final bullet here. The conservation of momentum classically corresponds to this little nugget of an equation down here. This sigma's a sum. The sum of the momenta of the particles is conserved. And here's the corresponding little nugget for relativistic particles. The sum of the relativistic momenta of the particles, gamma mv, that's conserved. So that's in a sense all there is to the difference between classical and relativistic momentum, and the ideas of momentum conservation still hold. Here's a picture that might help us think about what this means. So this picture, or this graph, is comparing classical momentum with relativistic momentum. And I've color-coded it. So classical momentum is in blue on the graph, it's mv, and relativistic momentum of particle is in red on the graph, it's gamma mv. So I'm just comparing these things. And the graph is to indicate the relationship, the connection between the speed of the particle and the momentum of the particle. So we're just graphing out how momentum depends on speed for some particle. Maybe it was an electron, or maybe it was a proton, or maybe it was a hydrogen atom, whatever. We're looking at the relationship between how the momentum depends on the speed, how the momentum is a function of the speed. This would not be a very interesting graph to plot if you just had classical momentum, because classical momentum P equals mv, P is proportional to v. This is a more interesting graph when you think about relativistic momentum, because P is not proportional to V. P equals gamma mv, and the little gamma, that little Lorentz factor, has a v in it too. So both the gamma and the v introduce dependence of the momentum on velocity. And so I'm plotting that. Okay, so here's velocity. And the range of velocities I'm plotting on the horizontal axis is from 0, nothing, it's at rest, to the speed of light, which is a maximum velocity we discussed for relativistic particles. So that's the range of velocities, and then vertically I'm plotting momentum. The blue line, that's classical momentum. That's just a straight line. That's just a straight line because P equals mv. P is just proportional to v. M is just a constant in P equals mv for any particular particle. So that's a straight line on this momentum versus velocity graph. But the relativistic momentum is not a straight line on this graph of P versus V. It's because in addition to the velocity depending directly on the velocity in the equation, P equals gamma mv, there's a velocity in the gamma of the equation, P equals gamma mv, and that introduces further dependence on V. If you're at low velocities, what did we say about gamma and low velocities? We got to know gamma a little bit in the last class, got to know the Lorentz factor, and that factor 1 over the square root of 1 minus v squared over c squared, it's essentially 1 if you're at everyday or low velocities compared to the speed of light. So at low velocities, the gamma mv equation is really becoming the mv equation, the classical equation, because the gamma is basically 1. It's only when the velocities become sizable compared to the speed of light or approach the speed of light that the gamma has an effect. And as the velocity goes up towards the speed of light, the gamma factor gets bigger and bigger. Remember the gamma factor of the astronaut traveling at 95% of the speed of light was over 3. So by then, you know, the gamma at 95% of the speed of light is having actually a stronger effect on the momentum P equals gamma mv than the velocity was. That's why, well, the relativistic momentum initially corresponds to the classical momentum at low speeds, gamma's 1, but then gamma starts to get bigger than 1, and so the momentum, relativistic momentum, gets bigger than the classical momentum. And so you see this effect here. And you see a really interesting effect happen as you approach the speed of light. As you approach the speed of light, gamma does a really weird thing. What gamma does is it gets bigger and bigger and bigger, but it gets bigger and bigger and bigger really fast. And as you get close and close to the speed of light, 99%, 99.9%, 99.999%, that gamma factor is blowing up. You know, it's 100, it's 1,000, it's 10,000. And so it becomes huge. And so the relativistic momentum starts to climb vertically and can never cross this speed limit. You see again the appearance in nature of a speed limit. Okay. Quiz question. I didn't forget. I ran out of time to give the quiz question in the last class. I'll credit everybody for that quiz question. I'll get it posted hopefully today, and you should check it out, but you'll get credit for last class's not given quiz question. So this is a question about what we've just been discussing. What have I just been discussing? See if I can remember. I've been discussing velocities, and I've been discussing momentum. And the question is, are there limits in relativity on the velocity of a particle? Are there limits in relativity on the momentum of a particle? Do they both have limits? Do neither have limits? All the combinations you can dream up. So I'll give you another minute or so to think about that. Well, this addresses that important discovery that we made in relativity about speed, that unlike classical speed, where there is in principle no limit to your classical speed, in Newtonian mechanics you could go as fast as you like, as long as you can build big enough car or big enough space rocket, you could go as fast as you like. In relativity, it's an amazing thing. There is a speed limit, and that speed limit is the speed of light. And light travels at the speed of light, and nothing else can go faster than the speed of light. And that's a remarkable thing about relativity. Momentum, on the other hand, I drew momentum. I drew both classical and relativistic momentum. This question is about relativistic momentum. And we saw that as the speed increases towards the speed of light, the momentum actually increased towards infinity. It becomes infinitely large if you could actually get to the speed of light. So there is a limit on speed. It is the speed of light for a particle. There is no limit on momentum. In principle, you can make more and more momentum. As you exert more and more force on a particle when it's traveling near the speed of light, it doesn't really increase its speed significantly. It just increases its momentum significantly. So that's a very strange effect. You're pushing on the particle, you're transferring momentum to the particle, you're growing the momentum of the particle, but its speed barely changes if it's close to the speed of light. Okay, the final item that I want to talk about, and this is a bit more lengthy than the momentum item that we just talked about, is energy energy in relativity. So we're going to discuss this for a bit. I want to start with this question, which is kind of a basic question, which is, what is mass? I'm starting with this question of what is mass because we're going to discover that mass is related to energy. And that's a feature, consequence of Einstein's relativity. So this was a great discovery that came out of Einstein's relativity. The most famous equation of relativity, the equation that everybody knows, right, is E equals mc squared. So this is where we were going to meet E equals mc squared. I said in the last class that, you know, the time dilation equation and length contraction equations were the most famous equations of relativity. I actually thought about it afterwards. I thought that was a ridiculous statement. Nobody, if I asked my mom, what's the time dilation equation, she's not going to know that, or length contraction, but she might know, I think she does know, E equals mc squared. So E equals mc squared is the most famous equation. I like to think of time dilation equation and length contraction equation as the foundational equations. If you've got a deeper appreciation, right, you now have a very deep appreciation of relativity, so you kind of enjoy those time dilation, length contraction equations. But let's get back to what is mass. So this is a picture, a slide of our developing understanding of what is mass. And it's an understanding that has developed over many centuries of scientific work, but it's also a developing understanding for us individually, because we're going to start up here in this corner. We're going to kind of walk across the top and then walk across the bottom here. It's kind of the order that we learn things in. Before we're 5 or whatever, you know. Before 5, our parents are really determining who we are and making us as crazy as we are. But in that time, we probably start to have a notion of what mass is, and that's where we start. Okay, upstairs here. One way of thinking about what mass is just a measure of a quantity of matter, a quantity of substance. Something with a large mass, like an elephant, has a lot of substance, has a lot of matter. Something with a small mass has just a little bit of substance, a little bit of matter, like the mouse. So an elephant, how much does an elephant weigh? I don't know, let's make the number up, 5,000 kilograms. That's a lot of mass. That's a lot of matter, a lot of substance in an elephant. How much does a mouse weigh, on the other hand? Let's make something up there too. Let's say 50 grams. That's a small amount of mass, a small amount of substance and matter. So that's kind of the basic elementary school definition of what matter is. Then there came more sophisticated scientific meanings of what matter is. The next one in my list here came from Isaac Newton, and it came from his laws of motion. Mass is in the laws of motion, F equals ma. And the role of mass in the laws of motion is it's an inertia of a particle. We think of mass as inertia. This is Newton's first interpretation of what mass is. It's inertia. And by inertia, I mean that inertia is the resistance that a object offers to a force trying to change its motion. So if you have a large inertia, large mass, you have a large resistance, reluctance to having your motion changed. So the elephant has a large inertia because it has a large mass, which means it's hard with a force to change its motion. It's running at you, you stick out your hand and stop it. It's going to just go right over you. On the other hand, a mouse that has a small mass, means it has a small inertia, a small resistance or reluctance to having its motion changed. Mouse scampering across the floor, it's easy to change its motion with a little force, and so that reflects its small inertia, small resistance, reluctance to having its motion change. So that's a new interpretation of what mass is. Think about it that way. So Newton also provided a second understanding of what mass is. And this is interesting because completely, in a way, completely different from inertia. Mass is the property of nature, the property of things, stuff that experiences gravitational forces. So the gravitational force between the moon and the Earth, which is the reason that the moon goes around the Earth, is due to the Earth and the moon's mass. The gravitational force between the Earth and the sun, which is the thing that makes the Earth go around the sun, is because of the mass of the sun and the Earth. The gravitational force between you and the Earth is the reason that you're stuck in your chair, is because that you and the Earth have mass. So it's the thing that causes gravitational forces. So a second Newtonian interpretation. Here's the one we're getting to. Came hundreds of years later, at the beginning of the last century. Einstein said that mass, matter, substance, is a form of energy, type of energy. Just like a form or type of energy might be kinetic energy, it's associated with motion, or a type of energy, a form of energy might be chemical energy, or it might be electrical energy. They're just types of energy. We've met electrical energy in electrical circuits in batteries. We've met chemical energy in electrical circuits in batteries. Well, Einstein's saying that the mass itself is also a form of energy. It's kind of equivalent to energy. Mass and energy are equivalent to one another. Mass is just a form, a type of energy. And so that was a consequence of relativity, and that's where E equals mc squared comes from. So we wrote down an equation for the relativistic formula for momentum P equals gamma mv. It just involved dropping gamma into the momentum equation. Now I'm writing down the same thing for relativistic energy. It also involves dropping Lorentz factor gamma into the equation, but it is a little bit more complicated, and it is a little bit more subtle, and there is a little bit more terminology that goes with it. There's things like total energy and rest energy and kinetic energy that I want to discuss. The energy, what I would call the total energy of a particle, relativistic particle, or even the total energy of a relativistic elephant or a relativistic mouse, if you can imagine that. That energy is given by this equation here. It's gamma. We're always going to get a gamma in relativity. So Lorentz factor times that thing we know, most famous equation, mc squared. So here's the mass of the particle, and here's the speed of light. So this is the total energy of a particle. It's a pretty simple equation, just like P equals gamma mv. It's a pretty simple equation for momentum, total energy of a particle, gamma mc squared. That's also pretty simple. One interesting thing about it is that if you look at that gamma mc squared, you don't immediately see the velocity in there, as if it didn't matter whether the particle is moving or not. But actually the velocity is in there. It does matter whether the particle is moving or not, because velocity is in the Lorentz factor. This total energy, this left-hand side of the equation, is often broken out into two distinct parts, two different parts with physical significance. One, Re, that's rest energy. That's an energy owned by the particle when it's just sitting on the desktop, or the mouse when it's standing there at rest, or the elephant when it's standing there at rest. And then the second part, Ke, well, you know that's the kinetic energy. That's the energy associated with the movement of the particle, or the motion of the mouse, or the motion of the elephant. So here we're breaking out the total energy of a particle into something that is always present, omnipresent, even when the object is at rest. Rest energy, that's a new thing, and a more familiar thing, energy that's associated with the motion of the particle or the elephant or the mouse, that's the kinetic energy. So we're just breaking out the fact that there are two types of energy. The rest energy, that's E equals mc squared. So that E equals mc squared. It's a little subtle, that E is the rest energy there. That's mc squared, rest energy. And then the remainder, well, look, if you've used up an mc squared over here, what do you have remaining? You have a gamma minus 1 mc squared. That's the kinetic energy. So this is the relativistic formula for the kinetic energy. So again, it has a gamma in it, which contains a velocity in it itself. And so that's how it depends on velocity. Okay. So this is really introduction to rest energies, kinetic energies, total energies in relativity. Just a few general remarks about it. So this rest energy is the famous E equals mc squared. Everything, you have rest energy, just sitting there, not moving. You have some rest energy. I have rest energy, the Earth has rest energy, an atom or a molecule or an electron and a proton. Well, they all have rest energies that are equal to m, their masses, times c squared. Now think about it. C is a big number. C squared is a really big number. 3 times 10 to the 8 meters per second squared. So that's a huge number. It's 9 times 10 to the 16. That means even the tiniest amount of matter, substance, mass, a milligram or a microgram or a nanogram, that actually has huge, huge, huge amounts of energy stored up, wrapped up in it. This was a breakthrough because it was a realization that the kinetic energy that we see of everyday particles or objects moving around is just a small, tiny, almost negligible contribution to their total energy. Their total energy is entirely dominated by their rest energies. And that rest energy is enormous. In a grain of salt, there's enough energy to power New York for a year, something like that. I made that up. But it's the kind of the scale of things. A grain of salt is a huge energy resource in its mass if you could get it out. That's what nuclear power does. It gets some of it out. It's actually what regular old burning of oil or coal or gas gets out too. It's just way smaller fraction of the rest energy that you get out when you burn coal, oil or gas compared to in nuclear power stations where they basically burn uranium or plutonium to make other atoms. Okay, so rest energy for everyday objects is huge, and then there's kinetic energy. The weird thing about the kinetic energy, I think, when you're faced is looking at this equation. Gamma minus 1 mc squared. Because I thought kinetic energy was half mv squared. When I was kind of comfortable with half mv squared, that was kind of warm and fuzzy. Now I've got a gamma minus 1 mc squared. That doesn't seem very warm and fuzzy. The interesting thing about it is that if you calculate gamma minus 1 times mc squared, if you take the limit of that equation. So a limit of an equation is when you take the equation to some extreme. If you take the limit of the extreme being the velocities being much smaller than the velocity of light, that gamma minus 1 mc squared actually turns into half mv squared. If you take that v much smaller than c limit. It's really interesting that it does that. First you say, well, I don't see the v in the first place. It's gamma minus 1 mc squared, but there is a v inside the gamma. Secondly, you might say, well, okay, maybe I can believe that, but what happened to the c squared? There's a c squared in gamma minus 1 mc squared. Where did it go? Well, it cancelled out in that limit. Got cancelled out. And so it's a fun project for a weekend of algebra to turn gamma minus 1 mc squared into 1/2 mv squared when v is much smaller than c. But it does do that, and so I wrote it down here. I just want to add a little appendix to this slide. I wrote it down here. This is the energy written in terms of gamma. It's the rest energies, kinetic energies, total energies in terms of gamma. That's one way of writing them. You can write them in terms of speed. You can write them in terms of momentum. I wrote down here the total energy in terms of momentum. This is another way you'll see relativistic energy written, but in terms of relativistic momentum rather than the gamma factor here. I wrote it down here because I think there's one. This is an often used equation, and there's, I think, a homework example that uses this version of this relation. Okay, I just wanted to make this point just to give you a scale of things. Let's think about the mouse. So let's imagine, how fast can a mouse go? Well, a mouse can sprint at 10, Usain Bolt of mice can sprint at 10 meters per second. You know, when it runs, at midnight, when it runs across the kitchen floor, it's 10 meters per second. That's the speed of a mouse. A mouse, what's the mass of a mouse? Well, it is about 50 grams, something like that. It's a tiny fraction of a kilogram. So knowing the mass and the speed, we can calculate the Lorentz vector if we like. We can calculate the energy, kinetic energy, and we can calculate the rest energy of the mouse. The rest energy of the kinetic energy of a 50-gram, 10-mile-an-hour mouse, I calculated it is half a joule. That's a little amount of energy. We've worked with joules before. The rest energy of a 50-gram mouse, whether it's going at 10 miles an hour or not, is 5 times 10 to the 15 joules. That mouse is a massive store of rest energy. It hardly has negligible kinetic energy at 10 miles an hour, or ultimately rest energy. Elephant. Mass of an elephant is 5,000 kilograms. How fast does an elephant jog? An elephant can jog at 10 miles per hour also. So let's calculate the kinetic energy and the rest energy of a 5,000 kilogram, 10 mile per hour elephant. And it comes out to be, for the kinetic energy associated with the motion, 50,000 joules. That's quite a lot of energy, right? That's why it's hard to stop the elephant. But it's rest energy. Well, that's really huge. That's 5 times 10 to the 20 joules, calculated based on E equals mc squared. So this gives you an idea of the scale of things in relativity, the scale of rest energies and kinetic energies of everyday objects. Kinetic energies, which are the things we notice, are just little tips of the iceberg compared to the rest energy. Oh, we got a visitor today. Albert Einstein's come to class. And so he's going to tell us about E equals mc squared. I think he's going to do that. Oh, that's not the video. That's the slide to advertise the video. Oh, but I got to get the sound on. Otherwise, this is going to be completely useless. Oh, I got to get the sound on here. Let me go back to the start.
That mass and energy are but different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is thought equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
So just thinking about what he said here, the first remark was really this idea that mass and energy are equivalent. So that came out of relativity, and that was established experimentally roughly 100 years ago now, that mass and energy are equivalent. So that was one important remark he made, and he sort of made the remark that the average mind doesn't really think about that mass and energy are equivalent, but that mass and energy are actually equivalent to one another. Then he also made the point, the big point, the scale of things, which is the amount of energy in just a little bit of mass is absolutely enormous. The amount of energy in a grain of salt is absolutely enormous, because E equals m times the square of speed, which is a really large number. Okay, let's look at an example problem. So this picture here is it's a picture taken in Batavia, which is kind of now a suburb of Chicago. So it's an aerial picture of a national lab in Chicago, or near Chicago. And it's the home of Fermilab, that's the name of the national lab, and it was the home of the US's largest accelerator. It was located at this lab. And like anything in the US, it's now switched off. But anyway, when it was running, this was the US's largest, highest energy accelerator, and they accelerated protons. You can see a ring here. And they would accelerate protons that went clockwise and also protons that went counterclockwise, and they hit one another, and we look at what happens. So that's what the accelerator was for. We're told that at Fermilab, in this accelerator, that the proton's total energy, when it got accelerated, sped up, was 400 times its rest energy. So that's the information we're given, that the total energy of a proton is 400 times the rest energy. And then we're asked to calculate the proton rest energy, the proton total energy, and the proton kinetic energy. So we're going to calculate these three things here. Let me make a couple of remarks first, though, before we do the calculation. It's pretty quick. First point is that the rest energy being, the total energy being 400 times the rest energy is the complete reverse of what I was discussing earlier on with the mouse's rest energy being much bigger than its kinetic energy, or the elephant's rest energy being much bigger than its kinetic energy, or any other everyday thing. For elementary particles like protons or electrons, it's not always that the rest energy is much bigger than the kinetic energy. Here's a case where it's vice versa. The kinetic energy here is much greater than the rest energy. So that's one thing. This is a new world then. The other thing is that I'm going to calculate these energies, but I'm going to calculate them not in joules because it gets cumbersome. I'm going to calculate them in another energy unit, electron volts. I'm assuming that you've had chemistry up, whatever, and you've met electron volts as a unit of energy. You've met electron volts over c squared as a unit of mass. They're better units of energy and mass than joules and kilograms for particles or for atoms or molecules. They're just much more convenient, and so I'm going to use them here. But just to hopefully remind us, 1 electron volt, which is a unit of energy, is this tiny fraction of a joule. 1 electron volt over c squared, which is a unit of mass, is this tiny fraction of a kilogram. And so I'll work with electron volts and electron volts over c squared. I'm running a little Not that this doesn't happen every single class, but I'm running a little late, and so I think I will skip the document camera, because that always costs me like 5 minutes while I switch it on, focus it, and do other things. Let's just go ahead and calculate rest energy, total energy, kinetic energy of our proton. That all we were told for the proton was that its total energy is 400 times its rest energy. But I did look up what its mass is. If you look up what its mass is, it's 938 million electron volts over c squared, which is 938. I'll write it as MeV, million electron volts over c squared. What's interesting is we were told that the total energy is 400 times the kinetic energy. No, we weren't. That's stupid. We're told that the total energy is 400 times the rest energy. That's a roundabout way of telling you the Lorentz factor. The total energy is gamma mc squared. The rest energy is mc squared. The total energy divided by the rest energy is just gamma. That is the Lorentz factor. And they told us the total energy divided by the rest energy was 400, because they told us the total energy is 400 times bigger than the rest energy. So they've told us gamma. And so that's a key thing to recognize in the question. Once you recognize that, the question becomes pretty simple to calculate these three energies here. Rest energy is mc squared. To calculate the rest energy, then I've just got to take the mass, 938 MeV over c squared, multiply it by c squared. Just c squareds will cancel out in the numerator and denominator. I get 938 MeV. That's the rest energy. Total energy. Total energy is gamma mc squared. Gamma, well, gamma is 400. We were told in a roundabout way the gamma factor. So it's 400 times mc squared. We already calculated mc squared, the rest energy. So it's 400 times 938 MeV. It's 375,000 MeV. That's the total energy of the proton. Then finally, kinetic energy. Well, look, that total energy that we know, part of it is rest energy. We know that. The other part of it, remainder of it, is kinetic energy. We don't know that. We can just take the fact that total energy equals rest energy plus kinetic energy, rearrange it for an equation that says that the kinetic energy equals the total energy less the rest energy. And so that was my final step here. Kinetic energy equals total energy minus rest energy. As an equation, it's this equation here. I don't need to use it. I can just subtract off from this total energy 375,000 MeV, 938 MeV, and I get 374,000 MeV. And so this is the kinetic energy here. I got one more example of energy. And you might want to take a look at that as a second example. It's about how nuclear power works. So in the way nuclear power stations work is that they convert mass energy into kinetic energy, which generates electricity. That's basically how they work, which is the same way that oil and gas and coal power stations work. They convert mass energy into kinetic energy to generate electricity. The nuclear power plants just do much more efficiently because they can convert a much larger fraction of mass into energy. Specifically, the way they do it is they take, as an example, uranium. They will take uranium, radioactive uranium, and they, in a chain reaction, they will split that uranium into two lighter nuclei. And it turns out that the mass of the original uranium is bigger than the mass of the two lighter nuclei. This is called fission. And therefore, the difference between the masses is the amount of kinetic energy that's released, and that's turned into electricity. So that's how nuclear power works. And I got one more example in here. It's this last slide. I've got no time to go through it, but it calculates the amount of kinetic energy you get out of one nuclear reaction. So This slide really tells you how nuclear power works, how uranium is burnt in a nuclear power station, like coal or oil or gas is burnt. It's burnt into these two lighter atoms or ions here, and in that process, mass is converted into kinetic energy, and you'll calculate the kinetic energy when one of these individual reactions occurs, and that's how we get a lot of our electricity. Okay, I'm going to end there. That was our last class on relativity. Next week, we're going to start, next week, the next 3 lectures is all going to be about light and matter, and understanding light and matter at a microscopic level. We're going to understand photons, electrons, protons. I'll hang out here if you've got any questions.